So, ladies and gentlemen, welcome to our first GOAT seminar of this semester. It's a pleasure for me to, as a first speaker of the semester, to introduce Radovan Červený and with his talk on kernels for dPaths Vertex Color.
Thank you very much for your introduction. Very lovely. In the next 40 to 60 minutes, I would like to tell you something about our joint work of me, Pratibha, and Ondra on some kernels for dPath Vertex Color. Yes, it's working. Okay, so let's start with the problem. What is the problem about? We are going to talk about covering some paths. So what is a dPath? dPath is a path of length d-1 or on d vertices. And we are going to say that the graph is dPath free if there is no dPath as a subgraph in that graph. And the dPath need not to be any induced subgraph. Yeah, any dPath in the graph will suffice. Then we can define the problem. The dPath vertex cover, or d-PVC in short, just takes as an input a graph, just regular graph and an integer k, and it asks us to find some small set S. The size should be less than or equal to k, that's our parameter, such that the set, if we delete it from the graph, we delete all the dPaths in the graph. Yes, what remains, it will be a PD-free graph. There is a short demonstration. So let's suppose this is our graph. As you can see, there are many. In this case, we are looking at 4 PVC, so we are interested in 4 paths. And for example, this is a valid 4 path. Yes. Please see that this edge would not be, or this edge is not included because we are not really looking at induced 4 paths. Any 4 paths as a subgraph will suffice. So this is the path, and we need to delete it somehow. So we can, for example, delete the vertex 4. We can, by doing this, we lower the budget by 1, and so on and so on. There is another path, and this one can be deleted, for example, by vertex 5. And as you can see, the rest of the graph is currently 4 path free. You can no longer find the 4 path, and we are done. So this is the problem. If we can find such a set, then we say yes. If such set does not exist, then we say no. But in this talk, we will be interested in something a little bit different. We'll be talking about kernels. So briefly, what is a kernel? Kernel is an algorithm that takes the instance, in our case, of dPath vertex cover, and the algorithm runs in polynomial time in the size of the instance, and it must return an equivalent instance to the original one. And an equivalent here means that if the original instance was a yes instance, then the reduced one will be also a yes instance. And if the original was a known instance, then the reduced one will be a no instance. And the third condition on the algorithm is that the resulting reduced instance should be bounded by some function of our parameter. So the kernelization algorithm somehow preprocesses the instance and should return some equivalent one, which is very much smaller than the origin. The typical building blocks of kernels or kernelization algorithms are reduction rules. You can see them as some functions or procedures that we can repeatedly apply to the graph if some conditions are met, and these reduction rules should somehow shrink the instance. And we will be talking about the correctness of such reduction rules, and the correctness, or also in the literature you can see safeness, means that the reduction rule produces an equivalent instance, and that's what we need to prove. We will give some set of reduction rules, and we will prove that they are correct, and then that they indeed run in polynomial time, and then we will be done. So this is briefly about kernels. And let's look at our results, what I'm going to talk about here. Known kernelization algorithms before us, there were known linear kernels for 2-PVC and 3-PVC. 2-PVC here corresponds to the very well-known vertex cover problem. So these are very good results. These are, I can say, asymptotically optimal. But for the general d-PVC, where d is greater than 4, nothing of this sort was known. Only these, I should say, general results were known because the dPath vertex cover is a special case of another problem, of more general problem called d-hitting set. So as you can see, the best thing that was known before us for d-PVC with d greater than 4 was that there were d times k to the d edges in the kernel. Yes, in the reduced instance, there were this many edges. Please note that the exponent of k includes the d, the parameter, or the constant of the problem. And how did we improve on this? We have managed to put together a general kernel for d-PVC that does not have this dependence in the exponent of k. So now it is just k cubed, and the d is put in front. So that is one great improvement. And then we were able to further shrink the size in the case for 4-PVC and 5-PVC. In this case, we can go up to quadratic number of edges, and that is actually something that we can think of as like, this is the best thing that we can hope for, unless something really bad happens. Yes, unless coNP is in NP/poly. Right, so these two results I'm going to try to talk about today. So let's start with the cubic kernel for d-PVC. What are we going to do? The high-level idea is, first we will find some maximal dPath packing in the graph. Maximal dPath packing is some set of disjoint dPaths in the graph. And then we will be marking some vertices and edges. And finally, we will have only one reduction rule: delete everything that was not marked outside the packing. So that's simple, right? Yeah. In order to prove the correctness, how to think about the correctness proof is assume that G is the original instance and G star is the reduced one. And any solution S for G will also be the solution for the reduced instance. But the converse may not be true. So if that's the case, that the converse is not true, then we can find in the original instance some dPath that is not covered by the solution. And we will show that either this problematic dPath either exists also in the reduced instance, which would be a contradiction with us finding a solution as S star, or that we can somehow modify the solution such that the problematic dPath is no longer a problem for us. That's the high-level idea. So very quickly, how do we find any maximal dPath packing? There is a simple greedy algorithm that just starts with an empty packing, and one by one, it finds some dPath in the graph and puts it in the packing and deletes it from the graph. If you do this repeatedly, until there are no dPaths in the graph left, you are left with some maximal dPath packing in the graph. This algorithm runs in this time, so in our case it runs in polynomial time. The exponential is in D. And few simple observations about the packing. If there are more than k paths in the packing, then the instance is trivial no. Yes, because our budget is k. So if there would be k plus 1 paths in the packing, they are disjoint, and you need at least one vertex per such path in order to solve the instance. So there will be only k paths in the packing, and the set therefore will be at most dk vertices in the packing. And of course, if you look outside the packing, all the components are dPath 3, Otherwise, we would be able to increase the size of the packing. So what are the dpaths that we need to deal with? We are not going to delete anything in the packing that we have found. Okay, so that's done. And there are no dpaths contained strictly outside the packing. Yes, the G prime sub I are the components outside the packing. So the paths that can be problematic for us must cross between the packing and outside the packing. And it may look like this. And how are we going to tackle this is that we are going to split the path into these segments. These segments always start in the packing and they cross outside, they do something there, and then they return to the packing. Yeah, so there will be a pair of vertices in the packing and some path between them outside the packing. And this is some segment that we will work with. Okay, so we need to get more structure outside the packing. So what we do is that we, for each component outside the packing, we pick an arbitrary vertex as a root, and we run a dFS traversal of that component from that root, which will give us these three structures. And since it is a DFS, the edges not in the tree will be only these back edges. And then some notation here, we are going to talk about the subtrees rooted at some vertices. And by that, I will mean in this picture, I will just look at everything that hangs below the vertex, and that will be a subtree. So we have this DFS traversal. And with that, we are now able to define something that we call a request. And the request is let's say it's a request for this pair of vertices that it wants some dpath or some path of specified length outside the packing. So for example, we will be looking at this request. The x and y should be the endpoints of the path, and the number 3 should be the number of inner vertices of the path that we want for this pair. And we will say that the request is satisfied by some vertex in the components, some vertex v, if there really exists such path in the subtree rooted at v and the endpoints. So for example, yeah, and what are we going to do? We are going to color the vertices of the components, and we will say that the vertex is yellow if the vertex satisfies the request. Otherwise, we will color it red. Okay, so what it means and what it actually means. Yes, this vertex will be colored yellow because if you look at the subtree rooted at this vertex, you can find this path with 3 inner vertices with endpoints x, y. So that's why this one is colored yellow. The same goes for this one. Again, you can find in this subtree, you can find some path that starts with x, then goes to this one, goes down here, and then goes to y. Again, 3 inner vertices. For this one, it's the same. You can find this path going here to R2, then here, and then back to y. Again, a path with 3 inner vertices. And the rest will be colored red. Yes, for example, in this subtree, there is no path that connects x and y through 3 inner vertices. That's why it's colored red. Okay, so once we do this, yeah, we pick a request and we do this coloring. And once we have this coloring, we will study the yellow forest that we have just created. So one observation about the forest is that if you look at the yellow leaves of the forest, then the subtrees rooted at those yellow leaves are mutually disjoint. And that's just the nature of DFS. So that means that for each such yellow leaf, we have a path of the desired length that connects the endpoints of the request. Yes, and with this in mind, we can look at this following procedure. If there are at least k plus d plus 1 yellow leaves, or I should maybe, yeah, okay, sorry. If there are at least k plus d plus 1 yellow leaves, we can just select arbitrary k plus d plus 1 of them. And for each selected leaf, we pick a path that satisfies the request in the subtree of that leaf. Yes, the leaf was colored yellow, so there must be at least one such path. So we pick any path. And we will mark the vertices and edges of this path together with the edges to the request. Yes, let me just skip to the next slide to tell you what I'm talking about. So this for example, our yellow forest, and for each yellow leaf, we know that there is some path that connects the endpoints of the request. And if there are many of them, then what can we say about the existence of this problematic dPath? Yes, we assume that the solution for the reduced instance in this case is not a solution for the original one. So can we really have this structure if this is the case? So what could have happened is that the solution somehow compromised k of these connecting paths on the segment. Okay, then it also may happen that the path itself, the problematic path itself, somehow compromised the paths connecting the request. But since there is at least one more, there will always be one that is free to reroute the segment of the problematic path. That means that if this is the case, if we can find the structure, then this path of the +1th yellow leaf must also be in the original instance. Hence the contradiction with the fact that the solution for the reduced instance was the solution for the reduced instance. Okay. Now let me go back. And yes, so that's the first part, the first case. If there are enough leaves, if there are enough yellow leaves, we do this marking procedure, and then we are done with the request. But what if there are not enough yellow leaves? In that case, we just mark all of the edges and vertices in the yellow forest, including the back edges, and we continue further. Okay. So let's say there are at most k plus d yellow leaves for the request. Luckily, the size of the yellow subforest is now bounded. As you can see, if you have only k plus d leaves, then the height of the tree is at most d. Then there are d times k plus d vertices in the tree. So when we marked all the vertices and the edges in the forest, we marked at most d squared times k plus d edges, or something like that. But there is still a problem. As you have seen, there are still some red subtrees hanging below the yellow forest, and we don't know how many of them there are, and we don't know their size. And that's what we need to address now. I'll maybe speed up a little bit over this part. We are going to basically do something very similar that we did with the request. The requests were some like wish for the pair that there is some connecting path, connecting the vertices with the vertices outside the packing. So we do exactly the same thing with the request. We split the path that should connect the endpoints of the request into some subrequests, and the subrequests in this case are of three types. It can start in one of the endpoints, then it goes to some red subtree, and then it goes to some yellow vertex. That's the first type. The second type is that it already is in the yellow vertex, then goes to the red subtree, and then immediately jumps to the second endpoint. And the third type is that it jumps inside the yellow forest. Like it starts in a yellow vertex, goes to the red subtree, and jumps to another. And what we aim to do here is that we need to mark enough vertices such that we can be always sure that such subrequests will be there, or that we can somehow modify the solution. Okay. So yeah, what we do with the what we now do with the subrequests and how the marking procedure works. We pick a subrequest, and for this subrequest, we count the number of red subtrees that satisfy this subrequest. And if there are more than 2D such subtrees, then that means that the path of the subrequests can be rerouted through these 2D red subtrees. Yes, again, the red subtrees are disjoint. And in that case, what can happen? The solution may somehow compromise some of these red subtrees so that this rerouting cannot happen. But once the solution picks at least D vertices from these red subtrees, we can move to the ancestors of the red subtrees and cut all of them, cut all of them away. Yes, I'm not going to go much in depth for this. It's rather technical, but that's the high-level idea. If you delete too many things in the red subtrees, you can move the solution from the red subtrees to the ancestors of the red subtrees, and you just cut away all the red subtrees, all like with one stroke. Okay, and then with this marking procedure, we bound the number of the red subtrees, and to bound the size of the red subtree, we just simulate all the possible ways the solution can interact with the red subtree. And again, we somehow stop at sufficient depth, and the sufficient depth is again 2D. And the same reasoning applies. If the solution would somehow delete more than D vertices in the red subtree, we again would be able to move the vertices to the ancestors of the red subtree and modify the solution such that the problematic path is again covered. Yeah. Yeah. The recursive procedure is somehow simple. We just start with an empty set, and then we pick any path in the red subtree that satisfies the request, and we mark all the vertices and edges of this path, because by this we mean that the path is somehow important for that request. And then for each vertex of this path, we recurse on it by putting it in the set S, which somehow means it signifies that we want to delete this vertex. For example, it simulates that the solution might have deleted this vertex, and then we recurse. Okay. Yeah. Okay. I have just joined these two slides together. Oh, so we may probably go over this one. And that's the high-level idea of the algorithm. And we can now do the final counting at how many vertices and edges we stem. So we start with the packing. As I said, we won't do anything to the packing. So we know that there is at most dk vertices in the packing, which gives rise to only quadratic number of edges in the packing. But there is also a quadratic number of different requests over the packing. Yes, any pair of vertices in the packing forms a request. Then for each request, we construct this yellow subforest, and we mark at most k plus d plus 1 leaves of this yellow subforest for the request. This gives rise to marking like at most dk edges and vertices for the yellow subtree. the important thing is that the k in here is linear for us. And then for each request, we had these subrequests. And for each subrequest, we picked some number of red subtrees and we bounded the size of the red subtree. But the size of the red subtree is now bounded only in D. There is no k in the size of the red subtree. So for each subrequest, it somehow leads to marking some d to the d vertices and edges in the red subtrees. But that's still okay because it does not depend on k. So together we have the edges of the packing. Then we have the edges of the yellow subforest for each request. And then we have for each request and each subrequest for that request sizes of the red subtrees together. And this together gives us some d to the d, but k cubed vertices and edges in the kernel. And that's what we wanted to show. Okay, so this is everything for the cubic kernel. Yeah, let's leave the questions after the second result, because the technique that we used for 4 PVC and 5 PVC is totally different from the first one. So you can take a sip of water and just clear your mind, and we can start over. So what are we going to? It's easier to grasp this result. So what are we going to do? We have these two simple reduction rules to start with. If there is a dPath reconnected component in the graph, we just delete it. We don't need it. And if there are more than 1 degree 1 vertices attached to some vertex, we again delete all but one degree vertices, such 1 degree vertices. Then we continue with still simple reduction rule. And for that, we need to define something that's called an adjacent matching. And it's just a matching. It's just a matching such that there is an edge between some given vertex and some endpoint of the edge in the matching. Like we pick vertex V, and then we find some matching for that vertex V, such that for each edge in the matching, there is a path connecting the vertex V and one of the endpoints. Let's say that the endpoint is A1 through AN. Okay, and the third reduction rule is if we find this structure in the graph and the matching is large enough, let's say that the size is at least k+2, then we can immediately delete this vertex V. And why is that? Because the edges of the matching together with V form many 4 paths or 5 paths in this case. And as you can see, these k+2 edges are disjoint from each other. So let's say we did not want to delete vertex V, then we would have to delete at least k+1 of these edges to delete all of the paths in the graph. That's something we can afford. Therefore, the rule is correct by deleting just V and lowering k by 1. Okay, now it gets a little bit more complicated, but still, it's a nice picture, right? So we need to somehow get more structure for the final reduction rule, and we will assume that the reduction rules 1, 2, and 3 cannot be implied. So that means that for each vertex V, there is the maximal adjacent matching to this vertex V is of size at most k+1. Yeah. So what we need is we have this vertex V, and we have some maximal matching adjacent to V. Yeah, I should say that finding such maximal matching can be done in polynomial time. It's no problem for us. So this is our setting, and then we look at what's remaining in the graph. The neighbors which are not the neighbors of V which are not in the matching will be called this set X. Yes, these are the neighbors neighbors of V that are not in the matching M. And there are some observations we can do about these vertices. One is that all the neighbors of these vertices must lie in the matching, or it is V. Yes, and why is that? Imagine that, for example, for this vertex, there would be some edge outside the packing M and not to V. We could just take this edge and put it in the matching, thus increasing the size of the matching. And this would lead us to contradiction with the maximality of the matching. Yes, and this idea can be somehow used in all of these other observations. We would always get into the contradiction with the maximality of the matching. So the same, there are no edges inside this set X. No two vertices in X are connected to opposite endpoints of the edge. Again, we would be able to increase the size of the matching, and so on and so on. And what we do now is that we split the vertices in X into 3 types. The first one are these vertices X2, and they are connected to some edge to both endpoints. They may be connected to something somewhere else, but there must be at least one edge to which they are connected by both endpoints. Then there is this type X0, X sub 0, and these are vertices that are not connected to the matching. In this case, they are the degree 1 vertices connected only to V. And the X1 vertices are the rest. Yeah. Final 3 observations before we go on. The sizes of these sets. The size of X2 is at most k plus 1, because there are at most k plus 1 edges in packing, and one of these observations forbids to have two vertices connected to both endpoints of the same edge. The number of vertices in X sub 0 is at most 1, because of reduction rule. I think it was 2. We deleted 1 degree vertices, more than 2 1 degree vertices connected to one vertex. And then if we assume that the degree of the vertex V is at least this, then we can say that the size of X1 is at least this, d minus 1 times k plus 1. Okay, so this is it. And what we are going to use is a tool called an expansion lemma. These are the definitions of the lemma, but we don't really need to go in depth. The expansion lemma gives us the following structure. If the conditions are satisfied, we will be able to find some vertices in our set M1. Yes, that I should have said, sorry. The set M1 are the vertices to which the vertices from X1 are connected to. Yeah, so that we know what are we talking about. And the expansion lemma gives us the following structure. It will pick for us some vertices from M1, these dark green vertices, and it will pick some edges going from these vertices to some subset of vertices in X. And in this case, we are looking at a 4 expansion of those vertices. And then that just means that from this vertex, there are some 4 edges going to 4 vertices. And for the other vertex, there will be other disjoint 4 vertices connected to or expanded from this vertex. And that's basically it. One more condition that's important to us is that the expanded vertices, their neighborhood lies in the dark green vertices. Yes, that's somehow it. So once we have this, we can formulate the reduction rule, the final reduction rule. Let the expansion lemma work for us, and let's assume that it gave us this structure. So from these 2 vertices, there are these 4 expansions, or in our case, in our general case, d minus 1 expansions and let this vertex X be some expanded vertex for some vertex in M prime. So the reduction rule for is simple, just delete this red edge. That's it. And why this should be correct? If you look, for example, at this vertex, its expansion and how it connects to V, you can find many 4 paths or 5 paths formed in between just these vertices. As for example, this right here is a 4 path. Or if we start in this vertex, go to V, then to X, then to the dark green one, and then back, we can find a 5 path. And we can use this fact in order to somehow force the solution to behave as we want it to. There are 3 cases that we need to address. Let's just go over them. We again assume that we have in our hands some solution S star, which is not a solution to the original instance. Hence, there must be a dPath in G minus S star. And this dPath must use this edge. And then we go over these 3 cases where the solution S prime does not contain whole M prime. In that case, we would be able, or in that case, if let's say this vertex is not in the solution S star, then hence we know that V also is not in the solution because the problematic path appeared at this edge. Then you can see that the solution must delete at least 2 of these vertices in the expansion. If it did not do that, there would be some paths in the reduced instance, and the solution would not be a solution, a contradiction. Yes, and once you solve these 3 cases, in all of these cases, we are able to somehow modify the solution, and the reduction rule works. Okay. And again, as before, let's do the final counting. So the sole purpose of the reduction rules 1 through 4 was to bound the maximal degree in the graph. Once we have that, the rest is somehow simple. So if the reduction rules cannot be applied, the maximum degree in the graph is d plus 2 times k plus 1. Okay. And what we do next, we again start with finding a maximal 4-path packing. This packing has at most 4k vertices and some k-squared edges. And since the maximum degree is bounded, the number of outgoing edges from the packing is again bounded. It's something like 4k times the maximum degree, right? So that means that there are k-squared components outside the packing, and all of these components are 4-path free. The 4-path free graphs can be described as of 2 types. They are either triangles or stars, and the stars, like single vertex is a 0 star, single edge is 1 star, and so on and so on. So there are only these 2 types, and we can show that in the case of stars, there can be only 2 vertices in the star that do not use any edge that goes from the packing. Yes, I'm not going to go into details how do we do that, but the fact is that only a constant number of vertices in the component outside the packing do not receive an edge from the packing. So that means that we can bound the number of vertices and number of edges outside the packing with this fact, and it amounts to this. It's again some constant times k squared. And the final sum is this very nice 176 k squared edges plus something linear. We don't really care about that. And the nice thing is that this technique follows, or this technique or the steps that we went through for 4PVC, they can be used for 5PVC almost in the same way. I tried to point maybe on 2 occasions how we would do that. But the only catch is that the 5-path free graphs have more structure. They have more structure. Let's end it there. But it also can be shown that there will be only constant number of vertices in the 5-path free components which do not receive some edge from the packing. So the same argument can be used. Yes, and the final count is again some constant times k squared. So that's what we wanted to show. So let me sum it up really quick. For 2-PVC and 3-PVC, linear kernels are known. Nothing better. You can just improve these constants here, but asymptotically they are optimal. For dPVC with d greater than 4, only the general kernel from d-hitting set was known, and we improved on that by removing the exponent dependence on d, and we just put a nice 3 in there. And we further reduce the number of edges for the cases of 4 and 5 PVC. So it's up to you to somehow discover if there is also a quadratic kernel for dPVC. We did not know how to do that, and if you somehow go over the technique that we used for the general kernel, you will find that there are some obstacles that make it problematic. Or I should say that the technique that we used for 4 and 5 PVC is problematic to adapt to the general case. You can probably see why if you go over that once more. And that's the end of my presentation. So this is now. Okay.
Well, thank you. Questions? Did you try the technique for 6 PVC and into some trouble there already?
Yeah. Yes. The trick is that for 4 PVC and 5 PVC, the matching gives you the structure that you need. But if you let me just show you. You would need something more than a matching for 6 PVC, because you won't find any 6 path in here, and that's the problem. We were trying to, like, instead of a matching, just use some maximal again free path packing. Yes, again with some edge sensitivity. But if you do that, then you lose this nice structure in the set X, or the structure becomes so rich that it's difficult to argue about it. So that's the obstacle, and that's also the obstacle that prevents us to moving to general D. Yeah. Thank you for the question.
Okay, maybe can I have a comment to that?
Sure.
Yeah, so in both of the cases, we start with the packing of dPaths, and we actually do not know like what to do, even if after you do the packing, all you're left with are isolated vertices.
Yes.
Even then, we don't know what to do.
That's true.
I mean, and for this 5 paths, it's that if you have 2 vertices with many common neighbors, you have a 5 path. This is not the case with 6 path. And it's the traversal.
Okay, so no other question. Thank you again, and let's meet in 2 weeks.
Yes.
2 weeks.